Hello guys, welcome back to another video on my channel. In this video, I'm gonna actually do an integral identity that will prove very useful to us. It will be a new addition to our arsenal. So with that being said, let's get started. We have before us integral and there's n of them from 0 to 1, 0 to 1, 0 to 1. So it's an n dimensional hypercube essentially that we're integrating on of an abstract arbitrary function f, which is a function of a product of the n coordinates that we're integrating on. So x1 times x2 dot 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 times xn. Notice the difference. We don't have f of x1 comma x2 comma dot 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 xn. It's a product of all the arguments. This is a general form of functions which have a product in their argument. And of course dx1 dx2 till dxn. This, and this is our claim, equals integral 0 to 1 f of u minus ln u, the quantity raised to n minus 1 over n minus 1 factorial du. So we're going to prove this by induction. To do that, we have to consider the base case, which is n equals 1. For n equals 1, we just have one integral from 0 to 1 f of x1 dx1 on the left hand side. And on the right hand side, we have integral 0 to 1 f of u minus ln u to the 1 minus 1 over 1 minus 1 factorial, which is 0 factorial. We have ln minus ln u to the 0th power, which is 1. So this entire thing goes away. And we have integral 0 to 1 f of u du, which, if you interchange the integration variable, since it's a definite integral, is the same as the left hand side. So LHS equals RHS, and that proves the base case. To move on, we have to assume the inductive hypothesis. So inductive hypothesis says that assume that this identity holds for n equals k for some arbitrary integer k. So we have to assume this equality holds when n equals k for some arbitrary integer k. That's the inductive hypothesis, is to assume this. But we're not done yet. We still have the inductive case to show that this actually holds for n equals k plus 1. We know it holds for 1, we assume it holds for k, and we show it holds for k plus 1. So, assuming 1, we know 1's true, 2 holds after we prove the inductive case, and then after that 3 holds and 4 holds, and then this holds for all integers. So for this, we start with the left hand side. We now have k plus 1 integrals, so 0 to 1, 0 to 1, a k plus 1 dimensional hypercube, and a function of x1 times x2 dot 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 times x k plus 1, with dx1, dx2, and dx k plus 1. Since we can assume the inductive hypothesis, we can assume this when we do the inductive case always, guys, remember, we can assume the inductive hypothesis. Otherwise, there's no real leverage we have when we're doing the inductive case. We have to isolate the k dimensional integrals. So we can remove the dx k1 integral, dx k plus 1, sorry, integral, and we have the rest dx1 to dx k integral in there. So we're 0 to 1 dot 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 0 to 1 f of x1 dot 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 x k plus 1, and the integrand is the same. It's just we have put brackets around the k dimensional hypercube integral here. Now we will redefine. So we will say g of x1 x2 dot dot xk is equal to what we had here inside this the red integrand here, so which is f of x1 x2 dot 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 xk plus 1. This helps us because when we plug this in here, our definition in this k dimensional hypercube integral from 0 to 1, we can actually use our inductive hypothesis because we know it holds for k. So we have, in this case, don't have an f, but we have a g, which is a function of the products of those k coordinates on a k-dimensional unit hypercube. So we can use the inductive hypothesis to just, instead of g, have g of u from 0 to 1 minus ln u to the k minus 1 over k minus 1 factorial du. And we still have the external integral here, which is on the dx k plus 1. So we have reduced our k plus 1 dimensional integral to a 2-dimensional integral on u and d and x k plus 1 just by using the inductive hypothesis. Now we can substitute for g. G of u, if you remember, if you go to the definition, is, well, if we call like this entire product x1, x2, xk as u, then g of u is equal to f of u times xk plus 1, because that was the term we were sort of omitting when we were writing the g. So when I do that, I have f of u times xk plus 1, and the same natural minus ln u to the k minus 1 over k minus 1 factorial du dx k plus 1. Now it will be in our benefit to change the coordinates. So let's set y equal to u times x k plus 1. So du is dy over x k plus 1. The left hand side therefore becomes integral 0 to 1 on dx k plus 1. That's unchanged. Is the u bounds and the u variable that's changing. So we have integral 0 to x k plus 1 f of y minus ln y over x k plus 1, the quantity raised to k minus 1, divided by k minus 1 factorial, times 1 over x k plus 1 from the differential element change, dy dx k plus 1. Now it might actually be easier to integrate on dx k plus 1 first rather than on dy. So we have to interchange the variables. The only problem is that the inner integral depends on the outer variable, which is xk plus 1. So to interchange the integrals, we have to actually draw the region of integration and then work accordingly by inverting the coordinates. So if we draw the xk plus 1 versus y plot, the region I have here in terms of these horizontal lines, these horizontal blue lines, is actually the domain of integration, with this vertical line at 45 degrees being y equals xk plus 1. So to change the variables of integration, we have to go from y going from 0 to 1, but the xk plus 1 has to go from y to 1, right? Because it starts here, which is xk plus 1 equals y, and then goes to 1. And the other one is essentially trapped in this unit square, so it has to go from 0 to 1. So if LHS equals 0 to 1, the integral y to 1 f of y minus ln y plus ln x k plus 1 over k minus 1 factorial, numerator is raised to k minus 1 k minus first power, times 1 over x k plus 1 dx k plus 1 dy. So all I've done here is just simplified this ln y over xk plus 1 using the quotient of arguments to difference of logs formula. So we have ln a over b is ln a minus ln b, essentially, is what we have here, with the minus sign compensated with the the minus from the quotient. And then we can, this is probably unnecessary for the experienced viewer, but I'm still changing variables. Z equals minus ln y plus ln xk plus 1, which is the term being raised to the k minus first power. dz will then become 1 over xk plus 1 dxk plus 1, which is just the factor that was hanging out there all alone. So the left hand side is integral 0 to 1 f of y, integral 0 to minus ln y, z to the k minus 1 over k minus 1 factorial dz dy. And then this is simple. Z integration over z is the most elementary integral you'll encounter. So we have integral 0 to 1 f of y, z to the k over k factorial, because we have k times k minus 1 factorial, which is k factorial, and evaluated at 0 and then minus ln y dy. We plug in the lny, because at 0 it's 0, so that doesn't matter. We have integral 0 to 1 f of y minus lny, quantity to the kth power, over k factorial dy. And this actually is the right hand side for the k plus 1 when n equals k plus 1. If you go back to the formula we had to prove, if you set n to be k plus 1, it's exactly the right hand side here. We'll have a k and then a k in the denominator, factorial as well. So this indeed proves that the left hand side is equal to the right hand side in the inductive case where we've assumed the inductive hypothesis. And that really proves it. So n times integral 0 to 1 of f of x1 times x2 dot 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 times xn dx1 dx2 dot 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 dxn equals integral 0 to 1 f of u minus ln u to the n minus first power over n minus 1 factorial du. And that's the identity we had to prove. Why is this useful? Because we can actually evaluate some integrals simply. The first example I realized later is a little more, it's easier to evaluate this integral using just the infinite geometric series. But I'll still go through this. I have another better example, so please bear with me. We have integral over the cube, unit cube, of 1 over 1 minus xyz dx dy dz. We can use the formula because you notice the integrand is a product of the coordinates that we're integrating on. So we have 0 to 1, 1 over 1 minus u, and minus ln u, quantity squared over 2 factorial du from the identity we proved. So we have 1/2. We can use infinite geometric series formula for this 1 over 1 minus u. So sum k equals 1 to infinity, integral 0 to 1, ln squared u to the k minus 1 du. And then just by parts twice essentially. So the first time we have 1/2 sum from 1 to infinity u to the k over k ln squared u from 0 to 1 minus 2 over k integral 0 to 1 u to the k minus 1 ln u du. So in this first term, we're actually integrating over the u, keeping the ln squared the same. And then the second, we're integrating over the u and also differentiating the ln. That's why we get the 2 and the k minus 1 in the u power du. And then, this first term, you can do L'Hopital's rule for the 0 case. It should vanish. The point is we repeat our integration, essentially integration by parts for this second term. So the 1/2 and the 2 will cancel. So we have minus sum from k equals 1 to infinity 1 over k squared u to the k ln u from 0 to 1 minus 1 over k squared 0 to 1 u to the k minus 1 du. You must be quite familiar with this kind of integration by parts manipulation if you've been on this channel as an avid viewer for a significantly long time. But it's just simple integration by parts. Use the DI method or whatever tic-tac-toe method you have, and you should get the same answer if you sit down and do it. The advantage is we integrate over this last integral because, again, L'Hopital rule argument makes this evaluation vanish. So we have sum from k equals 1 to infinity of 1 over k cubed, which, if you remember, is the Riemann zeta function of 3, which is basically undetermined. We can't express this in terms of any other transcendental or fundamental constants in mathematics. So we just leave it as Riemann zeta of 3, also known as Apéry's constant, essentially. Now, a better example of doing this, because you could also do this without knowing our formula, using infinite geometric series expansion. So you'd get sum from k equals 1 to infinity of x, y, z, quantity to the k minus 1. You'd integrate that. You'd get 1 over k 3 times. So that's 1 over k cubed. And that would just be the Riemann zeta of 3. A better example is integrating from 0 to 1, 0 to 1, sine of xy over ln xy dx dy. You use your formula that we have. So we have integral 0 to 1 sine of u over ln u, and we have minus ln u du. So we have minus integral 0 to 1 sine u du because the natural logs cancel, which is just cosine u integral 0 to 1 which is very simple to evaluate. It's cosine 1 minus 1. And that is a very nice use of this formula, because without this formula, you'd probably struggle to solve this, evaluate this. You'd never know what to do with this natural log in the denominator. And with integration, you're well aware, with anything that's in the denominator is essentially a work of the devil. You have to deal with it, you have to negotiate with it. Feynman parameter, Feynman or what is integration under the differentiation under the integration sign, which we call is dutis, the entire thing. With this formula, there's a significant ease. I will do probably another video from the Romanian Mathematical Magazine where we actually actively use this formula. So see you in that video. I hope you enjoyed this one. Peace out, keep doing math, and like and subscribe to my channel, guys. Peace out.